So I'm excited to be here on behalf of FIPI to give a short talk on carbon capture, utilization, and storage. So I'm currently working as a CCUS consultant at Wood PLC in the Houston office. So I'll start with a little bit or a background about myself. I just graduated with my master's in petroleum engineering from University of Texas at Austin. And before that, I was doing my undergrad in petroleum engineering from Pandit Deendayal Energy University from 2016 to 2020, right when COVID hit. And I've done some internships both during my undergrad and grad school. And that's what kind of helped me to come in this role at Wood PLC. So now I'll go to my extracurricular activities and leadership positions. I think I've just put this slide to emphasize how important networking is in our industry because our industry is so small that a lot of people know each other, and networking is a great way to build connections. And the way you can network is being a part of societies like FIPI, SPE. Wherever you get a chance, you guys should always try to network because through networking, you guys can meet different people and they can lead to opportunities that you can never imagine. Like I believe now PDPU has a Petrobol team. I think they've been participating into it. So that's a great way to build networks, travel around the world. And you might not believe it, but most of my internships or jobs were through networking, both at PDPU and at UT. So you should always try to come in front of people and talk to anyone, whoever it is, and build up your network in this industry. Because our industry is so small that you might be surprised that people know each other so well. So just wanted to stress on that. So now here's the outline for today's presentation. I'll be starting with an introduction to CCUS. Why do we need CCUS? Then going into carbon capture, geologic carbon storage. What are some of the impurities in CO2 storage? And then showing a couple of CCUS projects, what we've learned from those projects, and what role do we as petroleum engineers have to play in this energy transition. And then I'll be opening up the floor for any questions or comments you might have, not just on CCUS, but also grad school in the US or anywhere. And I'll try my best to answer any questions you have. So now moving into CCUS, what exactly is CCUS? So as I think the host mentioned, it is the process of capturing CO2 from point sources like gas power plants or maybe gas processing plants or directly from the air, transporting the CO2 either through a pipeline, rail, ship, and then either utilizing it for enhanced cell recovery or to build some building blocks or some chemicals, or either storing it permanently in geologic formations like reservoirs, aquifers for permanent CO2 storage. So that is the complete chain of capturing, transporting, utilizing, or storing the CO2. So why do we need CCUS actually? I personally believe that our industry, oil and gas industry, is extremely important to meet the energy needs of the entire world. And CCUS is indispensable, or we absolutely need CCUS to reach our net zero targets. So here I'm showing a plot about different scenarios of CO2 or CCS if we go by different policies. Let me start from the bottom. The first is the steps policy. What steps means is that if we have the policies that we have today, and if they continue to be the same for till 2050, we are only capturing like maybe zero point 0.2 billion tons per annum of CO2. Just to give you a context, our world currently emits like 36 gigatons of CO2, I believe, and that is like 36 billion tons of CO2 per annum. So we are not actually capturing or storing any or a very fractional amount of CO2. So that's not definitely going to help us reach net zero. Let us now look at the second curve, that is the APS. Now, APS means the announced policies. Like we've seen, or you guys might be hearing, a lot of governments are announcing their pledges for CCUS, saying that, hey, we are going to capture maybe 100 million tons or 150 million tons by 2050. So what this graph shows that if we were to go by the announced pledges, we'd be capturing around 3.8 billion tons of CO2 per annum and storing nearly 90 to 95% of that. But again, that is just 10% of the CO2 we emit. And then moving to the sustainable development scenario in the green plot, what that means is that they assume that the developed countries like the US, Europe, some countries in Europe and Asia, they'll reach net zero by 2050, China by 2060, and others by 2070. That will increase the CO2 capture volume to around 5.4 billion tons per annum. It's a good increase, but still not enough. And if we go by the Paris Climate Agreement, that is net zero emissions by 2050 for the entire energy sector, we'd have to capture 7.6 billion tons of CO2 per annum. And what we're doing currently is just 0.04. So we are off by a figure of, let's say, 200 or even more. And that is the scale that we need to get up to actually capture and store that amount of CO2 to reach net zero. So let us quantify CO2. It says that based on current scenarios, we need to scale up CCS to nearly 40 times in 2030. That is in the next 7 years, we have to scale 40 times. And in the next 25 years, we have to scale nearly 200 times. Now, this is a very interesting thing because for CCS, we are not actually making money. It's just like a garbage disposal process. No one is giving us money for that. So unless the government starts off providing any subsidies or tax credits to us, no company will ever want to make a loss by saying that, hey, we are going to capture and store the CO2. They need some kind of benefits like tax credits or a subsidy to set up these supply chains and set up capture plants, storage facilities. So a big government influence is needed or subsidies are needed in order to actually scale up CCUS. So let us look at the project status or the number of projects that have been going on in 2022. We have seen that from 2016 or 2017, there has been an increase in CCUS projects. And why do we see that increase? Because a lot of governments around the world, they're announcing some kind of a tax credit that, hey, if you are paying back $100 in tax to the government and you store 100 tons of CO2 every year, we are going to give you $20 back from your tax. Essentially, it's a saving that these companies get. And that is why they are like, okay, if we are getting some money back and also showing ourselves as sustainable or environmentally friendly, why not start CCUS? So that is the big driver that's actually increasing CCUS projects. And from 2021 to 2022, you can see that there are nearly 140 new projects announced in a single year. That is one of the biggest changes or the drastic changes that we have seen in this industry. And a lot of final investment decisions have been announced, around 15 in 2022. So I'm not sure if you're aware of final investment decision. What it essentially means that, hey, will this project go ahead or will this project not go ahead? So once they make a final investment decision, usually the project will proceed to the construction and implementation phase. And what we've also seen is a diversification of the market. Earlier, all of the CCS projects were done, or majority of them were done by natural gas processing plants, where they would just feed, they would just build a capture facility at the end of the natural gas processing plant, capture the CO2, and then inject it. Because earlier, there was not such a big market. But now, due to the new market that's opening up, we are seeing a diversification. What that is that natural gas processing is still 22%, but it's decreased a lot. And now we are seeing new industries coming into it, like the hydrogen industry, power industry, direct air capture, ammonia, cement industry, because everyone wants those tax credits back wherever there is a chance. And another interesting topic that we are working at Wood is CCS hubs. Earlier, what used to happen is that there was a single or single vertical CCS industry. So what happened was that there was one capture facility, one pipeline or one transportation facility, and a single injection site. So essentially, if the carbon capture facility is in maintenance or something went wrong, you are missing out on CO2 injection. So, and that had a huge risk on the one player that was actually operating, and huge liability both financially and regulatory wise. Because a lot of these tax credits are checked by the regulatory bodies, which I assume for India it would be DGH. So if DGH knows that if you promised 100 tons of CO2 injection and if you're not injecting it, then there would be some penalties coming in the future. So now what we've seen is CCS hubs. So now 10 operators or 10 different industries are saying, hey, let all of us capture carbon and deliver it to a single pipeline or a single transportation system. And all our carbon dioxide will then be taken through the pipeline and then injected. So what this does is it actually distributes the risk. Instead of one player taking all the risk, now 10 to 12 people, 10 to 12 different operators are taking that risk. So the risk is distributed amongst everyone, and everyone has less risk both financially and regulatory wise. So now what I've seen while researching on CCUS is that there is a lot of data available on how CCUS projects are processing. It's like, hey, there is a new CO2 pipeline network being built here. Where are the CCS or the capture facilities being built? What are the different storage options available? So you can see in this figure that there is so much data available that all of us can actually see how this industry is processing. And for importance and for relevance to us as petroleum engineers, there is a website, I believe it's not on here, but there is a website that actually shows full, like the petroleum engineering aspects, like the CCUS, well, injection well design, CCUS benchmark reservoir models that have been provided by real field data from operators like Equinor, ExxonMobil, Shell, to see how CO2 sequestration can be modeled. And these models serve as a benchmark to the industry. And that is going to benefit a lot of operators in what exactly to consider in future CCUS projects. So now I'll move on to carbon capture. There are three major types of capture facilities that exist. One is the post combustion, pre combustion, and oxy fuel combustion. So these are all relevant to industrial CO2 sources where you have a large or a good CO2 concentration. What I mean by a good CO2 concentration is like 15 to 20% of CO2. So going by the name, in post combustion capture, the CO2 is captured after the combustion or after the fuel combustion. And in pre-combustion, it is captured before combustion. And in oxy-fuel combustion, instead of burning coal or instead of burning the fuel, what we do is pure oxygen is used as the fuel. Now, what advantages do we have with post-combustion is that it can be easily retrofitted. What I mean by retrofitted is that it can be easily applied to any old power plants or any processing plants that is currently in use. You just need to put a capture facility at the end of the chain and you can capture the CO2. However, with pre-combustion and oxy-fuel combustion, it's very difficult to put it on existing power plants. This, for pre-combustion especially, you need to put it only in new constructions. Otherwise, it does not make sense financially or it does not fit the economics. You can only put it before the plant is conducted or before the plant is constructed so that you can set up the process. And in post combustion, the CO2 is removed from flue gas. So what's flue gas? Flue gas is like 85% nitrogen and like 15% CO2. So the CO2 concentration is less. So that's why we need more energy to separate the CO2. And pre-combustion, essentially, as the CO2 is captured before the combustion process, we would have purer CO2, but it's more expensive and it cannot be easily applied to current setups. Only if you're building something new, you can actually fit this pre-combustion facility. And in oxy-fuel combustion, as we're using pure oxygen, we get a high CO2 concentration, but it's both financially and energetically costly, and it's not financially feasible. The most common process that's been seen in the industry for existing plants is post combustion, where you can just put a unit at the end of the chain and you capture the CO2, and then you can do whatever you want with it. So once you've captured the CO2, how do you actually capture it? What is the mechanism that you use? So the four most common mechanisms are absorption, membrane, adsorption, and chemical loop. However, 99% of commercial projects or even most of the carbon capture projects use the absorption method. Why do they use this? Because it's been in place since a long time and it has been applied to commercials and it has been in the commercial scale, or we've seen field level projects applying absorption where we essentially used an amine to capture the CO2 and then heat it or reduce the pressure to separate the CO2. The other three methods are very promising methods, but they are still in the lab scale because the efficiency has not been developed to take them to the field scale. So a lot of research now is going into membrane adsorption and chemical looping because even though they are promising in the lab scale, we actually need it to go to the field scale because otherwise we've seen a lot of technological success in our industry, but not all of it is applied to the field. Why? Because in the end, we want to make, or our industry wants, or the company that we're going to be working for, we want to make money. We don't want to be, hey, we know this technology, but if this technology is not financially feasible, we are not going to apply it in the field. So now another interesting topic that's been coming up a lot in the news is direct air capture. So the methods that you saw earlier, they use CO2 with a high concentration, and high concentration is like 15% CO2. But in the air, the CO2 concentration is very less, maybe like 250 to 300 parts per million. So using these, the earlier processes for capturing CO2 is extremely unfeasible. So there's a novel technology called direct air capture. What this does is that it directly captures the CO2 from the air. So I'll show the process as in the figure. You have these large units with big fans that will pull the air into the unit. And then this air will pass through some filters which have some engineered chemicals, most commonly KOH, and that will essentially bond with the CO2. And then this bonded molecule will then be heated to release the CO2 and concentrated to be either used for some purpose or either stored in the subsurface. And then the CO2 free air will again be released in this atmosphere. This, however, is a very expensive method to capture CO2. However, a company called Carbon Engineering has been making great strides in this direct air capture. And an oil company based in the US called Occidental Petroleum is using carbon engineering's technology to build the biggest direct air capture plant in the world in West Texas that will capture nearly 500,000 tons of CO2 every year and use it for sequestration or enhanced soil recovery. So now let's move on to the most relevant part for petroleum engineers, CO2 storage. So as you can see from the map here, there is a huge potential for storing CO2 in the subsurface, especially because we as petroleum engineers have a lot of data and experience in the subsurface that there have been a large amount of sites that have been deemed suitable for CO2 storage. So let's have a deeper look into CO2 storage. So first I'll start with CO2 UR. So CO2 EOR has often been used as a conjunction to CO2 storage. So essentially, we might recover some of the residual oil and some of the CO2 will be stored naturally in the subsurface. We are not going to recover 100% of the CO2 we injected. And why is this such a popular method? Because this method has been in use for more than 50 years, CO2EOR. And it's like one of the talks I attended earlier. The company that is operating a CO2EOR operation, they been using CO2 for EOR since 1970s. And what it does is it gets miscible in the oil. What I mean miscible is that it completely dissolves in the oil and makes it like a single phase if it's perfectly miscible. And then it essentially takes off or it essentially vanishes the interfacial force, leading to additional recovery of the residual oil. And this is if we inject it above the minimum miscibility pressure so that the CO2 is actually miscible with the oil. And then in this process, because none of our floods are obviously going to be perfect, so there is always some amount of CO2 that's going to be left behind in the subsurface. Why this option makes sense for us is that because we are extracting some additional oil, we can make money with this. So because in CCS, we are not actually making money from anywhere. So by producing some extra oil, we can make some money by selling the oil. So that is a very promising option for CO2 storage because essentially CCUS also means utilizing. And here we are utilizing the CO2 for sequestration or enhanced cell recovery followed by sequestration. So let us look at what are the different options for CO2 storage. I'll be talking about that in more detail in the next slides. So we have depleted oil and gas reservoirs and then using it for CO2 EOR. Then we have deep saline aquifers, coal seams, and using the CO2 injection for extra methane recovery. So what happens is that once the CO2 is injected into coal seams, excuse me, it gets adsorbed on the coal seam, and this leads to release of methane, which can be produced for our energy needs, and the CO2 gets adsorbed in the coal seam for sequestration or storage. There are also some small options like basalts, oil shales, and cavities, but not a lot of research has gone into that. So now let's look at aquifers or reservoirs. What makes the most sense for us? So with aquifers, because the entire planet has so many aquifers, we have a significant amount of storage capacity in aquifers. By aquifers, what I mean is not groundwater aquifers because we are not permitted to actually inject CO2 in groundwater aquifers. What I mean is extremely deep saline aquifers where the salinity level, nearly 10,000 ppm or 10,000, a TDS of 10,000 total dissolved solid content of 10,000 ppm, which is far more than we can handle. So those kind of aquifers are identified suitable for CO2 storage because we don't want to put CO2 in groundwater aquifers. That would just reduce our drinking water or potable water sources. And another is depleted reservoirs where we have high storage capacity because we've extracted a lot of oil and gas from these. So there's a lot of space left behind. And for CO2 EOR, we have the option of producing oil, which can pay off some of the cost associated with the project. Now in aquifers, the main concern that we have is that we have not been drilling wells in aquifers. Like in oil and gas industry, we don't want to penetrate an aquifer. Like we don't want to produce water for fun. So we don't actually have a lot of data in deep water or saline aquifers. We do not know if there is a seal present. So we should be checking that, hey, where we are injecting CO2 and where the CO2 is going to be migrating, is there a seal present to actually stop the CO2? However, in depleted reservoirs and CO2 UR, this oil and gas has been stored under the seal for millions of years. So we know that there is a seal present there that can hold the CO2. And we've drilled close to hundreds to thousands of wells in these areas. So we know that, hey, we can we have a lot of data around on these reservoirs, and we know that there is the presence of a seal to actually store the CO2. In aquifers, another disadvantage that we have is that we are not actually producing anything from the aquifers. We don't want to produce saline brine or such brine from deep aquifers. So essentially, we are injecting into a closed system, and the pressure is going to just shoot up. And we have to be very careful that we do not exceed the fracture pressure, because otherwise the rock will be fractured and the CO2 will just leak. That will just defeat a purpose of injecting CO2. And however, in depleted reservoirs, we have a lower reservoir pressure, but that has some disadvantages as well. What it can do is CO2, when we are trying to inject CO2, we essentially want it to be in a dense phase. However, if there is a low reservoir pressure, there is a severe Joule-Thomson effect. What it does is that the CO2 will expand rapidly, and there will be the presence of multi-phase flow in the tubing or in the reservoir, and that can lead to hydrate formation and a lot of problems. And also in aquifers, if your aquifer has or is extremely saline, what it does is that the CO2 will react with the salt or the saline brine and will form like a solid salt structure around the wellbore, and that will lead to a big loss in injectivity. And then you have to stop CO2 injection, do a workover with the hot water circulation every now and then again restart, because you want to dissolve the salt, because that is just going to stop your injectivity. So let us look at the life cycle of a CO2 storage. So again, there are four main aspects of CO2 storage. One is site selection. Now, this is potentially the most important aspect of CO2 storage, because we want to inject CO2 in a site which can accept CO2. Like it should have a good porosity, permeability to actually allow the CO2 that we want to be injected and not have rapid pressure buildups or fracture the rock, and have good injectivity. I'll show you an example in the later slides where there was a formation that just couldn't take CO2. So essentially, the engineers had got it all wrong, and they had to urgently find another site for injecting CO2. Then is the well construction and integrity. Now, CO2 is an extremely corrosive fluid. So, if you use normal oil and gas equipment for CO2 operations, it's going to corrode away the tubing, the downhole components. So, what we need is specialized equipment for CO2 storage equipment or CO2 storage wells. And essentially, if you try to understand that in oil and gas reservoirs, we usually what we have is the higher production during the early stages. So the highest stress on the wells is essentially during the start of a oil and gas production system. But in CO2 storage, it's actually the opposite. The highest stress on a well actually exists at the end of CO2 storage, because you're injecting for 30, 40 years. And then at the end, you have to plug and abandon the well and ensure that the material or the well is robust enough not to allow the CO2 to migrate through the well. So that is something very important in CO2 storage well construction. And then monitoring programs. Now, CO2 monitoring and verification is extremely important, because we want to see where the CO2 is going. And we do not want the CO2 to come back to the surface or go into some formations which we've not seen. And also, this has a big implication for getting back the tax credits that you apply for, because the government is going to see, hey, is your CO2 going out of your awarded area, or is it in the same area as you wanted it to be? And is the CO2 migrating anywhere? If yes, then you have to pay a penalty, because you are essentially putting the CO2 in a dangerous zone to be exposed to the surface. So that is something very important. That is from a petrophysical perspective, petrophysics and geophysics perspective. And then finally, when we close the operation or when we end the operation, you typically in the US, Canada, and other countries, you have to monitor after 15 years or till 15 years after the injection stops. So you need to see that the CO2 is stored, it does not moving outside our area of interest, and it's not leaking at least for 15 years after the CO2 injection is stopped. Otherwise, there are big penalties for CO2 leakage or migrating outside the area of interest. So, what actually happens to the CO2 in the subsurface? There are four main mechanisms which actually act on the CO2. The first is structural and stratigraphic trapping. So, this is the most common mechanism. What it does is that once you inject the CO2, your CO2 is going to be typically lighter than the brine. So, it's going to migrate to the top of the structure and then be stopped or blocked by the cap rock or the stratigraphic trap to allow or to not allow the CO2 to migrate towards the top. Then what you have is residual trapping. As you all know that most of the rocks would be water, preferentially water wet. So what it would essentially do is that some of the CO2 that we injected is going to be trapped as an immobile phase in the middle of the pores. So that is referred to as residual trapping. The third is solubility trapping. So you see these bubbles that are trapped in the middle of the pores. These will slowly dissolve in the formation brine, leading to the formation of carbonic acid. And that is called the solubility trapping mechanism of CO2. And finally, this carbonic acid will react with the rocks and lead to the formation of minerals like calcium carbonate, dolomite, and CO2 will essentially turn into a solid. And that's what we eventually want. And once it turns into a solid, it does not move. So that's essentially our end goal. So now let us look at the different trapping mechanisms and how they come into effect and how secure are they. We can see that the most secure mechanism is mineral trapping and the least secure mechanism is structural and stratigraphic trapping because essentially the CO2 can move in structural and stratigraphic trapping. However, in mineral trapping, it cannot move. But if you look at the time scale when mineral trapping comes into effect, it's like 100 to 1,000 years. So you can see that that's why we need monitoring and verification programs because the CO2 is going to keep moving, going to keep migrating at least for 100 to thousands of years. So what we can do is we want to have a robust monitoring program to see that we have a good cap rock and the CO2 is not migrating anywhere where it shouldn't be migrating. That is something that's very important in CO2 trapping mechanisms. So now let me go to some projects or some big CO2 sequestration or CCS projects and what we've learned from these projects. So the first one is Sleipner, Norway. Now this was the one of the first CO2 injection projects, the CCS projects that started in the world. And this started like 27 years from today in 1996. And this was based in Norway, operated by Equinor, earlier known as Statoil. So why was this project started first of all? So Sleipner was a gas producing field and it had large amount of CO2. What I mean by large is around 9% CO2. And from Norway standards, they could not sell the gas with such a high CO2 content. They had to reduce it to nearly 2.5% CO2. So they thought that instead of paying a penalty, why not we capture the CO2 and then transport it and store it in a saline aquifer. So this field was nearly 250 kilometers away or offshore and at a water depth of 80 to 100 meters. And they were injecting into a saline aquifer. So what Equinor thought was that there are 8 layers, as you can see in the figure, where the CO2 might migrate eventually. And the CO2 injection point you can see is at the extreme bottom. Now, what happened was suddenly they realized that there is a mystery layer where the CO2 is going, where you can see layer 9 in the left figure, and you can see on the figure on the right, where at 800 meter, there is a big layer of CO2. Now, they were surprised that this layer we did not take into account into our simulation and screening studies. So where did this layer come from? And it was thankful that they had a big layer of cap rock over it. So the CO2 did not migrate to the surface. But the way they missed this layer, and because CCS might lead, or it might lead to, some CO2 migration to the surface, and this might be catastrophic for CCS projects. So that is why this was very important, and they missed it in modeling. So this is a thing that we should be aware about to see what formations can we actually inject CO2 in. So now moving on to Snøhvit project, again a project operated by Equinor based in Norway, again CO2 injection into a saline aquifer. And here the challenge that the experience was that the storage capacity was far lower than studies expected. So what they thought is that we can inject maybe CO2 for 18 years at maybe 1 million tons per annum. But what they realized is that after 1.5 or 2 years, is that the formation is not taking CO2 and the pressure is building up to dangerous levels, or the pressure is building up so high that it can lead to rock fracturing or the fracturing of the formation. And that is something we do not want in a CO2 storage project, because the CO2 will then just keep on migrating. So now they had taken up a lot of contracts for CO2 capture, and now they had to urgently find a third spare formation where they could actually inject the CO2. And that led to an extra $225 million of capital expenditure cost, just because they did not estimate that this formation is suitable for CO2 injection or not. So it needs to have a good porosity permeability, and we should have a good amount of spare pressure that it can take in order to not reach the pressure limits, because CO2 injection is a process that will go on for 30, 40 years. And we need it to have a good storage capacity. Otherwise, it's of no use to inject CO2 here. The third and last project is an Insala field in Algeria. Again, a same case of high CO2 or a rich CO2 gas, and they had to separate the CO2. And they were injecting into a saline aquifer as well. Now, what they did not do is they did not do appropriate screening. So what happened is that once they started injecting, just 18 months later, they realized that, hey, the pressure is so high. And when they did their first monitoring study, they realized that they had actually fractured the cap rock. Now, this is something we absolutely do not want, because this can be catastrophic for a CO2 injection process. They were thankful that the cap rock was so thick, nearly 950 meters thick, that it did not actually cause any damage. But what they saw was that the ground surface was elevated by nearly 20 to 25 millimeters, and because of CO2 injection and the high pressures that it induced. Now, again, you can see that all these three case studies I presented had some challenges because adequate screening, simulation, and testing studies were not actually done on these projects. So these three fields there are many cases, but these three fields have a great lesson that adequate testing, screening, and simulation should be done to actually see if a CO2 or if a formation is suitable for CO2 injection. So what are the different considerations? First, we should be absolutely sure that the cap rock above the reservoir is impermeable and does not have any communication channels with the surface. Then the CO2 mobility, where exactly the CO2 is going to be going. Then in the case of aquifers, we should be monitoring regularly pore pressure buildup, because we are not taking anything out. There's always the chance of cap rock fracturing, seismic activities. So additionally, there should be very frequent 3D seismic surveys to see where the CO2 is going, and pressure tests to see how the pressure is looking. Another interesting technology that has been developed in Iceland is called carbon dioxide mineralization. What it does is they essentially inject CO2 dissolved in water, or CO2 with water, into igneous rocks like basalt. And basalt has some minerals that accelerate the conversion of CO2 into solid. So what it does is that what they claim is that 95% of the injected CO2 is converted into rock in 2 years. However, it's only possible in igneous rocks like basalts, and they are very deep. So this is a challenging yet interesting technology that's coming up. And I think a lot of researchers are moving into this technology to see if actually carbon dioxide mineralization can be speeded up. Because if this happens, you're essentially making the CO2 immobile. So that's the best case scenario for us. So another important topic is impurities. What I always like to say in this is that CO2 or CCS is like a garbage disposal project or a garbage disposal process. All of you might be throwing away or disposing some garbage every day from your homes or your hostel rooms. And most probably, it might be the case that every day or every single day you might not have the exact same garbage. So you'll always have some variations in your garbage. And if we are capturing CO2, it's very rare that we capture 100% pure CO2. We'll always have some impurities like nitrogen, argon, hydrogen, oxygen, some impurities. And these impurities have big implications on CO2 transportation and storage. Transportation wise, they make the operating phase envelope for us very narrow to operate in. So there's always a chance of hydrate formation, increased hydrate formation, multi-phase flow. And in the case of storage, what happens is that it reduces the density of the fluid that we are injecting. So essentially, our storage capacity is reduced. So we cannot inject the same amount of CO2 if we have some impurities as compared to pure CO2. So this is a topic in which a lot of universities, I believe, are doing research, especially from the transportation perspective as well as the storage perspective. The last part is what skills do we have as petroleum engineers that is applicable in the energy transition? And here I'm going to generalize based on, I think, CCUS, geothermal, and hydrogen storage. I believe these three energies are going to be very important in us moving to a lower carbon energy future. And all these three technologies have important roles for us as petroleum engineers. Because in all of these, we are going to need reservoir engineers for reservoir simulation, well testing, understanding the subsurface, because all of these involve the subsurface. And our industry has more knowledge and more experience in the subsurface than any other industry. For the drilling and well engineers, we are going to need a lot of wells to store the CO2 to extract geothermal for hydrogen storage. And these fluids, some of these fluids are extremely corrosive, and they need your expertise or our expertise in actually building or drilling robust wells and completions to actually sustain corrosive fluids or actually extract geothermal or stored hydrogen. For production engineers, I might analogize it to injection, because most of the processes in production, like flow assurance, nodal analysis, we need that to go in injection as well to see how the CO2 injection, or what's the phase, or is there multi-phase flow during CO2 injection, or how's the injectivity looking like in CO2 injection, or even hydrogen storage or geothermal. And facilities, we would need large scale facilities in all of these processes, and we need expertise of petroleum engineers or our industry, because we've been operating these facilities or these large scale processes for nearly 100 years now, and we have the expertise to carry it forward to this industry or the energy transition industry. So I personally believe that oil and gas is a great role, still an important role to play. But I think with the energy changes, or with the changes that is going on in the energy transition, you guys should have some knowledge about this lower carbon future, CCUS, geothermal, hydrogen, because a lot of companies in India as well as in the world, are going to go big on these technologies. And just having these skills or this transferable skills is going to make you ready for the energy future that's upon us. With that, I think that is it from my side. And I'd be happy to open up to any questions or comments you might have about anything that I can answer on. Thank you, everyone, for listening.
If anyone is having any doubt, they can unmute themselves and ask the question one by one.
Is there, I think, oh, there is a
So there is
question
one
from,
question. Yes, sir.
yeah,
Can you discuss the
yes,
safety and
yes.
environmental consideration related to carbon capture, transportation, and storage?
Yeah, that's a great question, Om. And I think that's very important, especially for the general public, I believe, because here, I think in Europe and the United States, there are a lot of people who think that CCUS is not beneficial for the environment. There are obviously going to be safety concerns, especially while CO2 transportation through pipelines. Because if we are transporting large amounts of CO2, and there is a problem or a small brittle fracture in these pipelines, then these pipelines can burst, and extremely high CO2 concentrations are going to be dangerous or harmful to people living in and around the place. So there are always going to be safety concerns. But what I've seen from statistics is that transporting CO2 is relatively safer than transporting oil and gas. But again, we need to be extremely careful when designing facilities for CO2 transportation. And for storage, I believe that especially if you have not done your due diligence on evaluating assets or evaluating storage sites, then there's always a chance, as you saw from these field projects, that some CO2 might come out from the surface, and that just defeats our purpose of storing CO2. So that is why it's still a hit or miss with the general public. But I think our industry, especially the oil and gas industry, has the expertise to lead the CCUS industry. I hope that answered your question. Oh,
Yes, thank you so much, sir.
yeah, no
So
problem.
there's one more question.
Yeah.
What are the key considerations for choosing suitable sites for carbon storage, and how do we ensure the long-term integrity and safety of stored carbon?
Thanks, Gautam, for the question. That's a very important and an interesting question. So, the main aspect or prior to CO2 injection for storage is that it should or we should be doing a lot of well logging analysis or geological analysis to see that, hey, if we have a reservoir that is suitable for CO2 storage, we need to have the presence of at least two seals or two cap rocks above it. That's what the regulation is, at least in Canada and I believe the US, that there should be the presence of a primary cap rock and a secondary cap rock to ensure that the CO2 does not go or does not migrate. And after we started injection of CO2, usually we've had to do seismic studies or like 3D seismic studies every couple of years or say every 5 years. And from that, for every 3D seismic study, that kind of translates to 4D seismic. And we can see exactly, or we can make a good estimate on where our CO2 is today, where it is after 2 years, where it is after 5 years, and see the extent that where our CO2 is migrating. So that is how we monitor the CO2. And integrity wise, again, we have to do multiple studies to see that if there are some wells in the area that are not properly plugged and abandoned, that might lead to CO2 leakage. So we need to take all those considerations into effect before actually starting CO2 injection. Because end of the day, we do not want to get in trouble with the regulatory authorities, and also we do not want any CO2 to leak from the subsurface. Yeah. I think there's one more
So that,
question.
yes, sir. After doing CO2 based EOR, do we again extract CO2 from produced fluids in which CO2 has been completely mixed, and what are the methods to do so?
Yeah. So after doing CO2 based EOR, the oil or the gas that we produce, it has some amount of CO2 mixed in it. And we cannot sell the oil and gas with say 5 to 6% CO2. We need to get it down to 1% or maybe 2.5% before actually we want to sell it to a downstream or a midstream operator and then to the refining unit. So what they have is that they have these what do you call GGS? I think if you've heard in ONGC or these batteries or early production systems, they have these plants here or small capture facilities there to actually separate the CO2 before sending off the oil and gas to the refining unit. And then this CO2, separated CO2, is again recycled back for injection. So it's like a recycled process where the CO2 you captured, it's then again recycled back for again CO2 injection. And this cycle continues on.
Okay, so one more question.
Yeah. Yeah.
What are the safety issues to be taken care of while trapping CO2 in ballistic basaltic formations like carb fix in Iceland, implementing it?
Yeah, so that's a great question. I've not had a big chance to read about it. But I would say that if what they're saying is true, then actually it's a very safe method, I think, because essentially the injected CO2 is essentially just getting turned into solid within 2 years. So essentially, all of our CO2 is trapped. But the safety issue we might have is, or not a safety issue, but from an injection point of view, I believe that basaltic formations have very low porosities and permeabilities. So we might not be able to inject as much CO2 as we want to inject. So I believe that may be a challenge. But again, I'm not exactly sure of the different safety issues. So I'll try to read up on it and get back to you if that's okay.
Sir, if
In touch, yeah.
this is a cyclic process, then how we are reducing carbon emission at global level?
Yeah, so that's a great question. So earlier, when this CCUS industry was not coming up, we didn't want to actually, because at that time, CO2 was not captured from some anthropogenic facilities. What it was done is that what all these companies had is that they had the CO2 rich reservoirs, which produce some natural gas, and they cannot sell the CO2 rich gas. So they just separate the CO2 and then use it for injection again and again so that they do not have to buy CO2 for EOR and thereby improve the profitability of the project. But now what happens is that in CO2 EOR, every time we produce some gas or oil, the CO2, it will have, say, suppose in the first time you produced it using CO2 injection, it might have, say, 5% CO2. And the next time you produce, it might have, say, 4% CO2. So some CO2 approximately is getting stored in the formation. So earlier, when we used to do CO2 UR, it was not for CCS purposes. It was just that some CO2 would be stored there. But now, as we are doing more and more for CCS projects, we are trying to store more CO2 than we actually inject, or the we are trying to store more CO2 with every CO2 EOR cycle. So earlier it was just getting stored for, and we didn't want to extract it again. And this was not for carbon emissions at that time. This was just to produce oil and save the CO2 that we have to buy again and again. So now we are using it specialized or specifically for CO2 storage purposes. And earlier, it was not at all about CO2 storage. It was just about EOR and nothing else.
So next question is, for
Yeah.
successful CO2 EOR approx, how many times of PV CO2 required to inject, and what is the average cost of injecting 1 meter cube of CO2, because it affects the techno economics of project?
That's a great question, Vishal. So, what I believe is that CO2 EOR, at least from what I've read, it's never done as pure CO2. So what typically is done is that they do water alternating gas. So they inject a slug of CO2 and then they follow it up with water, because it was never, I think it's injecting WAG is a much successful project, or is a much successful process of extracting residual oil, because once the CO2 has found a gateway through some high permeability zone, then essentially all the CO2 that you're going to inject will just be produced. So what they do is follow it up with some water, and they have these alternating slugs of water, CO2, CO2, water, CO2, water, to just kind of follow it up for extra oil recovery. And the basis of cost, I think, for 1 ton of CO2, I think CO2 is much easily measured in mass terms. So for injecting 1 ton of CO2, essentially from the capture to transportation to storage, it would take nearly $90, I believe, $90 to $100 if we have a good source of CO2. And what the government gives back as a tax credit is, like in the US here, it's $85 per ton of CO2 you inject. So essentially, I believe that you are in no profit, no loss stage now, because and as this technology is going to scale up, the cost is going to go down. But for from a mass perspective, it takes nearly $90 to $100 to capture, transport, and store 1 ton of CO2.
Okay, sir. Thank you, sir,
Yeah.
for delivering this valuable knowledge to us and sparing your valuable time for us. Thank you, audience, for patiently attending the webinar and making it successful one. You may all leave now. Thank you.
Thank you so much for inviting, and sorry to have spoiled the important match today. Yeah.
No
See you
problem.
guys. Yeah, if you have any questions, yeah, no worries. If you have any questions, you can reach out to me on LinkedIn or any other platform. I'd be happy to answer any question. Okay.